Here, and today I'm going to add some complexity to these type of problems so far, and I believe on the courses that you have seen so far in this program, you are assuming that your duration for each task are deterministic, meaning that you know the duration with 100% sure. So if you say the duration of the project or the task is 5 days, you're assuming that that's not going to change. Today we're going to basically change that, and we're going to have some stochastic times, meaning that you don't know for sure how long it is going to take. You're going to have some estimates, a positive estimate, a normal estimate, and a pessimistic estimate, and we're going to use that information to try to compute our critical path. And you're going to see how will that affect our final decision in terms of deciding how long it's going to take the project, and also how can we deal with the customer when you have this type of situation. So we're still on objective number 5 for the class, which is create and analyze network diagrams to identify opportunities for reducing the project lead times. And the agenda for today is, first, we're going to calculate the activity flag. So I know you should be familiar with that already. And then we're going to talk about the project uncertainty and how to manage that risk that is going to be due to this project uncertainty. So we're going to calculate probabilistic activity times. We're going to develop a probabilistic network, and we're going to compute the probability of completing the project on time. And then we're going to decide based on the risk what will be that estimate in terms of the duration of your project. So we have a couple of things that we actually need to cover today. So the learning objectives are the same from our previous lecture. So we're going to basically focus on this part today on the stochastic conditions. So now we are not assuming that we have deterministic times. We're going to have stochastic conditions, meaning that we're going to have some estimates, and the durations of the tasks or the projects are not known with certainty. So before we get to that point, let's just review very quick what we did last time. So we were able to develop two types of networks, an AON and AOA network. Here I have an example. So you have this information, you have the predecessor, the activities, and also the duration. So from that we can develop this type of network, in where we have a node representing the activity and the duration. From here we can find the critical path and the critical time using this information, and this was part of the exam. You needed to identify this earliest start time, earliest finish time, latest start time, and latest finish time for one of the networks. And we're going to use this one more time, this notation, for our analysis today. So in terms of finding the critical path, you know you need to find those earliest start time, earliest finish time for each one of the activities. So we did that already. So you know that if you have a predecessor, the earliest start time for those nodes are going to be the earliest finish time of the predecessor. So we can perform same type of analysis, and from here we can determine that the critical time is going to be 21 units, because it's the longest that it's going to take to complete the project. And we can go back. So all activities and all tasks will be completed to finish the project. So the shortest path to completion of the project is equal to the longest path through the network. So going back, we can identify the latest finish time and the latest starting time. And that's the information that we're going to use to determine the slack of the activity. So the critical path for this example is highlighted here in gray. Okay, so now let's start with the new material for today. And again, I'm sure that you are familiar with calculating the slack. This should be something that you have seen in a previous course from this program, but let's just review because this is important for what we're going to cover next. So to calculate the activity slack, this is the amount of time. One second. The amount of time a non-critical task can be delayed without delaying the project. This is called a slack or float. The slack for any activity can be calculated using this notation. So if you can identify this for each activity, then you can compute the slack by two ways. One way is the latest start time minus the earliest start time, or this is going to be equal also to the latest finish time minus the earliest finish time, and this equals the slack. Okay, so if you have this information, you can subtract the latest finish time from, or the earliest finish time from the latest finish time, or you can use these two to compute the slack. Any questions? Okay. So for any task on the critical path, its latest finish time, let me put that here, should be the same as what? If you are in the critical path, this latest finish time should be equal to something. So that will be the earliest finish time, correct? Because if you do that, then you'll get 0. So it therefore has 0 slack. If it finishes later than its earliest finish time, the activity will be late, causing a delay in the project. Okay, so that makes sense, right? If you have a critical activity or an activity in the critical path, then you know that the latest finish time should be the same as the earliest finish time, and you will have a 0 slack because those are the activities that you cannot move. That will affect your duration of the project. So for example, let's refer back to this network, and we're going to focus on activity I. So that's the activity here. So activity I could be completed as early as day 18. So that's the earliest finish time, because its earliest start time is 12 or day 12. And it has a duration of 6 days. Okay, so we can gather that information from here: earliest start time, earliest finish time, and the duration. It must, however, be completed by day 21. Or the project will be delayed. Because right now it's saying that the critical path or the critical duration is 21. So if we don't complete that activity by day 21, the project is going to take longer to be completed. And because I has a duration of 6 days, it cannot be started later than day 15, which is the latest start time. Okay, so if you want to complete this activity by day 21, then you know that the latest that you can start this activity is day 15, because it's going to take 6 days to be completed. So using this information, just put this here, 21 minus 6, that's 15. So given a latest start time of 15 and the earliest start time of 12, task I could be delayed up to how many days? So we already mentioned that is the difference between these two, right? So it's going to be 15 minus 12. So that will be 3 days, without affecting the completion of the project. So if you look again here, you have the earliest start time. So this is the earliest that you can start the task, and this is the latest that you can start the task to get the total duration of the project. So the difference of these two will give you the slack. So activity I has 3 days of slack. Any questions? So for that case, that's very simple. You don't have any activity depending on that specific task. So for instance, if you were looking at this one, which is what we're going to do next, you have 2 activities depending on that one. So the analysis must consider those 2 activities. So let's look at activity B. So following the same type of analysis, task D must be completed by day 12. And that's by looking just at this first. Let's look one by one. I know you can see that you have this activity that needs to be started earlier on the critical path. So first, let's look at that portion of the network. So it must be completed by day 12. So that has not to make G late and thus date late, and thereby the whole project late. Thus, along this path, task D has 3 days of slack in the role as a predecessor of task G. But now we're going to look at the other. Go ahead. Yes, I'm focusing first on that portion of the network. Now we're going to look at this one. Okay? So, yes, it's going to be 11 because that node is dependent on this one. So now we're going to look at the other portion. So we're going to focus on this part now. So, but this is also a predecessor of critical activity H. And along this path, task D must be completed by day 11. Or H is going to be late. So, this is going to be our determinant task. So task D therefore has only 2 days of slack, not 3. Because again, you can see that 11 will be the latest start time based on this activity. Any questions? Okay, so Again, deterministic times, very simple analysis. Just have to make sure that you're using the right numbers and that you're getting the right information from the network. So in terms of the managerial implication of the critical path and the slack, the project manager's primary attention must be paid to the activities on the critical path, and that makes sense. That's what's going to determine the duration of your project. So if anything delays one of these activities, we know that the project will be late. So you will focus your attention as a project manager to the critical path. And this raises an interesting question. So you know that for some activities you're going to have some slack, meaning that you might have some flexibility in terms of the resources that you have available to complete those tasks. So the question is, can any resources reserved for use on B be borrowed for a few days to work on A and thereby shorten its duration? So what we're trying to say, for those activities in which you have slack, can we move people from those activities and put it into the activities that are doing the critical path longer and try to shorten that critical path? Well, the nature of these resources in A's technology will dictate whether or not this is possible. So the answer is it will depend on the task, but that's something that you can consider. So if you have extra resources and you have some slack, you can try to move some resources from those activities and try to shorten the length of the critical path. So if A, for example, could be shortened a day by using B resources for 4 days, the critical path will be shortened by a day. So that's something that you can consider as a project manager. You can try to see if you can move some of the resources and then try to shorten the critical path. Any questions? So now we're going to transition to the interesting portion of this lecture. And for me, this is very interesting. This is actually part of my research. Most of the models that we have developed in industrial engineering are assuming that we have deterministic information. So you know for sure, you're assuming that you know for sure that you know the duration of the task, you know everything, and that's not going to change. But in reality, that's not true. So what you're going to be dealing with in the industry is with estimates. And those estimates are going to be based on historical information. So that historical information is something that already happened, and you're trying to plan ahead by using that historical information. So you know that your analysis is based on information that is already in the past, and that will not tell you for sure what's going to happen in the future. It could give you an idea, but you are not 100% sure that that's what's going to happen. So that being said, we're going to look at project uncertainty and risk management. And this part of the lecture will actually use part of the material that you learned in class in probability and statistics or engineering statistics in IE 320. So calculating the probabilistic activity time. So assume that all possible durations for some tasks can be represented by a statistical distribution shown here. So now instead of saying the task duration is going to be 6 days, we're going to use the historical information and we're going to create a statistical distribution to model that duration of the task. So if you have, for instance, a data set for the machine failure rate or the machine duration for completing certain products, you can use that information and create a statistical distribution for those time durations, and then use that information to represent or to model the duration of the task. So we're going to use this statistical distribution to model the time duration. And the mean of this distribution, or the expected time, can be easily found using the following equation. So we're going to estimate the mean using time duration estimate going to be equal to A plus 4 times M plus B divided by 6, where A is optimistic estimate, M is the most likely estimate, and B is the pessimistic estimate. Okay, so this expectation or mean is going to be for this type of distribution, and the shape of this distribution that we are using for this analysis is the beta distribution. The reason we are using the beta is because that distribution is very flexible, so it can take very different shapes and it can accommodate different type of data structures. So this calculation gives an approximation of the mean of a beta distribution and the beta distribution is used because it is far more flexible than the more common normal distribution. So most of the time when you're dealing with the expectation, the expected value, or the mean of a distribution, you're going to end up working with the normal distribution. Anyone remember why from your course in statistics? So if you're dealing with the mean or the expectation, you have multiple means, and you're trying to find the distribution of the mean, why we end up having a normal distribution? There's a reason for that. Actually, it is because of the central limit theorem. So what that theorem is telling you is that if you have multiple means and you plot the mean, and I actually can give you an example, but I can bring that in later. You will end up having this shape. Which is the shape of the normal distribution. So every time you're dealing with the expected value and you're trying to find the expected value, the distribution of the expectation of the distribution of the mean, you're going to end up having a normal distribution, a standard normal distribution because of the central limit theorem. So, but we're going to use both actually. We're going to start with the beta, and we're going to estimate the expectation using the beta distribution. But then we're going to have to use the information that we have, which is going to be a list of expected values and a list of variances, to find a probability. So at that point, since we are dealing with the expected values of multiple data points, we're going to use the normal. Okay? So I don't want you to get confused. The important thing here is we're going to estimate the expected value of the distributions using the data. And then, using those expected values, that list of averages, we're going to find the probability of completing the project using the normal distribution. So we can approximate the standard deviation, or sigma, of the beta distribution as follows. So sigma is going to be equal to b minus a divided by 6. And this is a equals optimistic estimate, b equals pessimistic estimate. And this is for when you are accounting for 99% of the sample. So at 99%, we can estimate this standard deviation of the beta. We can also use the estimate at 95%, and that sigma will be equal to b minus a. So this is a b minus a divided by 3.3. So today I'm going to assign you a homework, and you're going to have a problem in which you're going to be using the 95% estimation of this standard deviation. So I want you to use this one instead of this one. Okay? So the following table shows a set of tasks, their predecessors, and the optimistic, most likely, and pessimistic durations for each activity. So here we have, instead of having just one column telling you that this is going to be the duration of the task, we also have a couple of estimates for those lower bounds and upper bounds. So you have a range of values for each duration or for each task. We also have the predecessors for each one of the tasks. So the information that we have in this table is very similar to what we saw earlier, with the only difference that instead of having just one number telling you the duration, now we have 3. Now, we already learned how to compute the expected value of each task. So we're going to assume that this data is going to follow a beta distribution. So we can estimate that expected value, let's say for activity A, using the equation. So we have 4 times m plus b divided by 6. So for that case, we have 8 plus 4 times 10 plus 16 divided by 6. So this equals 64 divided by 6, which is equals to 10 over 6 days. So it's almost 11 days. Okay, so using this information, we are estimating or finding the expected value of the duration of that task. And that's only for A. So this is using this information. We can also estimate the variance. So for this case, I'm going to use the 99% formula. So we have B minus A divided by 6. The formula we got was for the standard deviation. So if I want to compute the variance, what do I do? Anyone? Yes. You have to power to make a square. Okay? So it's not the square root, it's make it to the power of 2. So the variance is going to be that. So we'll get this value from here. So we're going to use the estimate, the pessimistic, and the optimistic. So it's 16 minus 8 divided by 6. That to the power of 2. So that will be equal to 1.78. Okay, so now we have the expected value and the variance for the first activity. We can repeat the process for each one of the activities. Can I move to the next slide? Just wait for it. Yes, sir. 3.3. Yes. So if you repeat the process for each one of the activities, this is what you're gonna obtain. So we have the expected value for activity A, B, C, D, and up to H. So we have the duration and the value. Okay? So now we're gonna use this information to find our critical path. Okay? So as you can see, it's not going to be that simple because now we take into account those two estimates for each one of the activities. So if you put that into the network, then we have the duration and the variance inside the node, and we can actually repeat the process just using the effective value for the duration to get the total expected duration for the network for each one of the paths. So, for example, we started here. For A, we have 10 times 4 over 6. B, represented by this number. Z here, and so on. You can also observe that, for instance, activity D has no variance. Yes, sir.
So in like the homework and things like that, you want us to have in this form, we have the 2 over 6 at the end, or?
You don't have to use the fractional values, you can use decimal points. Yeah, but most likely they're not going to be integer numbers. You're going to have some decimal
I
points.
just get a preferred way
No, you can put it in this way, but I think it's going to be easier just to use the decimal point. Good question. So I just wanted to look at this activity for a second. So you see that the estimates for pessimistic, normal, and optimistic are the same. So you're going to end up having no variance. That type of activity could be something like a machine process in which you are certain that you're going to have a specific duration if the machine doesn't fail. So that can also happen. But for the rest of the activities, you have the estimates are different. Now, we have a duration and a variance, and we can also proceed to get the critical path. So in this case, it's going to be A, B, D, G, and H. And we're going to have a critical duration of 47 units. And that's only based on the expected value. So the expected time for each activity is used to find the critical path and critical time for the network. So in this example, that will be 47. So the critical time is 47 days. Now, since these are estimates, can you tell your customer that you're gonna have your project ready in 47 days? I'm sorry. No, right? Because you know that there's some variability involved in this estimate. So 47 days, again, is the expected number. And we want to know, and that's what we're going to do next, with which probability, and if the probability is high enough, to tell the customer with this certainty we're going to have the project ready in this many days. So because the mean time T is used for all the activities, there is a 50-50 probability of completing the project in 47 days or less, and also 47 days or more. So right now the analysis is not telling you much. Like you have an expected total time or critical time, but you don't know with certainty, or you don't know with a specified probability or chance if that's going to be the actual duration. So recall that the project has an expected critical time of 47 days, and that's for the path A, B, D, G, and H. So how would you respond if your boss said the client just called and wants to know if we can deliver the project on April 30th? This is basically 51 working days from today. I have checked and we can start tomorrow morning. So let's say, just forget about this, and then you have 51 working days from today, and you can start working on that project right away. What would you say? Would you be able to complete the project with the estimates? Would you be able to tell your boss that, oh yeah, we can have that ready, we're going to have some time? Exactly. Still, we are dealing with estimates, and we cannot tell with certainty, yes, we're going to have the project ready in 51 working days. So, path AVDGH has an expected duration of 47 days, but if you promise delivery in 47 days, there is a 50% chance that this path will be late. And that seems to be too risky. So to complete the project by a specified time requires that all the paths in the project network be completed by the specified time. So again, remember that not only the critical path is based on estimates, the other paths in the project are also based on estimates. So we need to make sure that for this type of problem, and also in reality, that when we are dealing with these estimates, that all the paths must be achieved within the time required. So therefore, determining the probability that a project is completed by a specified time requires calculating the probability that all paths are finished by the specified time. Okay, so far we have used we have assumed that the time duration of these tasks are going to follow a beta distribution. We basically, what we did was we gathered the data of duration, we put it into a Minitab or another distribution fit. We got a good fit for the data, and the software is telling you that the data is following a beta distribution. So we had that estimate. We know the task durations are going to follow the beta. So we can use the expected value of the beta to find the estimate duration for each one of the tasks. So that's what we have done so far. We estimated the expected value of each one of the tasks, and we found the variance for each one of the tasks. And we are assuming that all tasks are going to follow a beta. That gave us information to compute the critical time based on the estimates. Okay, so we have that information already. Now, what we are interested in knowing is, based on those estimates, can we tell our customer we're going to finish the project by this date with this probability? So I'm 95% sure that I'm going to complete the project in 51 days. That's the type of conclusion that we want to get now, based on the information that we have. And that's what we're going to discuss next. So calculating the probability that all paths are finished by the specified time. So again, I'm going to refer back to your course on statistics, i.e. 3320. Recall from this course that the probability of multiple independent events, all occurring is equal to the product of each event, individual probability of occurrence. So what we are saying is, if you have a dice and you throw that dice, the probability of getting a 1 is going to be the same as the probability of getting a 6. Those are independent events. If you want to get the probability of getting a 1 and a 6, then you know that you need to multiply those two probabilities. So in that case, it's going to be 1 6 times 1 6. So that's the probability of those two events happening at the same time. So what we are saying for this particular problem is the probability of having all the paths satisfied by this number of days is the probability of satisfying one path, the probability of satisfying the second path, and so on. So we're going to multiply each probability, and we're going to get the probability of completing the project. Okay, and this will make more sense with the example. But hopefully you can see that what you learn in this class in statistics is useful, because you're going to be using that in some of your coursework, including this one, and also as an engineer in the future. So if you didn't got part of the material, or if you thought that you were not going to use that information that you got in that class, yeah, you were wrong. You'll be using that a lot. Okay? So, for example, let's evaluate the probability that path A, B, D, G, H, which is apparently the critical path, will be completed on or before 50 days after the project is started. So we can find the probability by finding Z. Z again denotes the random variable for the standard normal distribution. So if you remember from stat class, we were using Z and we're estimating x bar minus mu divided by sigma. And we're using this value of Z, let's say 1.96, to find the probability from the normal table. So we're going to use that and we're going to apply that here. So Z is the standard normal random variable, and we're going to estimate that probability using that. So we can find that probability. Z is going to be equal to D minus mu divided by the square root of sigma square of mu, which is the variance of the random variable. So this is essentially this, with the only difference that D now represents the desired project completion time. Mu is the sum of the expected activities times of the path being investigated, and this is the variance of the path being considered. The sum of the variances of the activities on the path. If you move to the next slide, then you will see the table for the normal. If you took the class IE 3320 from me, then you probably saw that table. Well, I'm 100% sure that you saw that table because I passed it around and we discussed that table in class. So here it is again. So this is the probability for the normal probability distribution, and we have the table for the standard normal. So you can find the C value using the column and the first row, and the probabilities are going to be inside the table. So the exact nature, we put here, the exact nature of Z will become clear now, shortly, using the problem in hand. Mu equals 47 days. We want to find out if we can complete this project in 50 days. So D is going to be 50. And the variance, or sigma squared of mu, is going to be equal to 1.78, which is the variance of activity A plus 0.25 plus 0 plus 4.0 plus 1.36, and that's going to be equal to 7.39 days. So we are adding the variances of the task in the critical path. So if we take the square root of that, we can get the standard deviation. So that will be the square root of 7.39 days, and that equals 2.719. Okay, so using the standard deviation, the D, or the completion time, and mu, we can find the value of the z random variable. So that's 50 minus 47 divided by 2.1. Can anyone check this calculator? Anyone has a calculator with you and check if this, because I have two numbers for the square root. I want to make sure that I have the right one. So what's the square root of 7.39?
3.719.
3.7?
3.719, that's right.
Okay, 719. Okay, so this one's, thank you. So this z value is going to be equal to 1.10. So now, using the z value, we can get the probability of completing that path in 50 days. So 1.10, we can go here in our table, right here. It's 0.86. So for 1.0 is going to be this number. Because z value is 1.10, so 1.1 and 0, that tells you that you have a 86% probability of completing that path of the project in 50 days. So that's going to tell you, so the probability 0.8643, or about 86% that this path will be finished on or before day 50. Okay, so for that path, we can tell there's an 86% probability that we can finish that before day 50. You can imagine what will happen if you increase this number from 50 to let's say 70. When you compute that probability, that should be almost 100%. Okay? So, but we are not done. We only have the probability of one of the paths. So we need to repeat this process for each one of the paths in network. So similar calculations are next done for paths A, B, C. So that's going to be this one, C, F. And for A, B, E, H. And we already have the computations for this one. So we have, oh yes. So we have that one, and we are missing that one. Sure. So we have these two, and then the last one. So in total, we're going to have 4 different paths, and we need to repeat the process for each one of the paths. We already have the critical path, so if you repeat the process for the other 3, this is what you're going to get. The probabilities of each of these paths being completed by day 50 are 98.5%, 97.8%, and virtually 100% for the last one, respectively. So based on this, the probability that the entire project will be completed by day 50 is calculated as bonus point for anyone who can tell me how can you compute it. No?
You just add all together.
I just said it, yeah. It said it before we started the exam. Yes, you multiply it. You have to multiply the probabilities. Remember the example of the dice, 1/6, 1/6, multiplying to get the probability of both happening at the same time. So the probability of all of them happening at the same time is the multiplication of all of those probabilities. So in that case, that will be 0.864 times 0.985 times 0.978 times 1.0. That's going to be equal to 83.2%. So based on our analysis, the probability of completing the project in 50 days is about 83.2%. So that gives you a better idea in terms of your planning. So if you want to have a certainty of 100%, then you know that you need to expand your time frame. Any questions? Okay, so next we have one more thing to cover, and it's very related to this. Assume that the client is very important, very demanding, and will be very upset if the project is late. The client has asked when the project output would be available. The client insists on a firm date. How sure do you wish to be about being on time? Carefully considering the matter, you decide that you want a 95% probability of meeting your promise completion date. So you want to have at least a 95% confidence that you will be able to complete that in a certain number of days. When should you tell the client to expect the delivery? So we can perform a similar analysis to get that number. So this is the same problem solved just a few seconds ago, but now D is the unknown, while the probability associated with Z is preset at 95%. So basically what you're going to do is to solve for D using the same analysis. So referring to the normal table, we can see that for a 95% probability, C will have a value of 1.645. So therefore, Z equals D minus mu divided by the square root of sigma squared mu. This is 1.645 equals D minus 47 divided by 2.719, and D is going to be equal to 47 plus 1.645 times 2.719, and D is going to be equal to 51.5 days, so about 52 days. So with the 95% confidence, you can tell the client that you need 52 days to complete the project.
So we just added 2 days on that and changed our confidence from 83 to 95.
Yes, to go from 83 to 95, and you need to add a couple of days. Yeah.
That's like.
Oh yeah, for sure. Yes, and then again, you want to make sure that you are satisfying the client, but you don't want to compromise your work at the same time. So you have to find that balance. So I guess that's the last thing for this lecture. Any questions? So you're gonna have a homework based on this. What is the tendency? So all of you who signed in today will get a bonus point for the next exam. Just for coming to class today. I really appreciate you putting the effort. I can tell you it's gonna pay off by the end of the semester. Okay, so keep your good work and make sure that you work on your homework. And I'll see you on Tuesday. Anyone else needs to sign in? The homeworks, please check the homework. If you are one of the students who didn't put the name on it, just let me know, and I will add the score to my grade sheet.